Section 6.2 starts delving more deeply into parallelograms. This section is somewhat long, and look how long that outline is. It doesn't help that the last bullet point is added to this section, as it seems a bit out of place. But that's where the book has it, so we will roll with it. Most of this stuff isn't hard. There is just a lot of little things to get through. So let's get to it. First, the definition. A parallelogram is a quadrilateral with both pairs of opposite sides parallel. This is definitely a parallelogram. You can probably see where it gets its name from with all of those parallel lines. But what about this? Does this one count as a parallelogram? It has a ton of opposite parallel sides too. You don't nearly see it as often as the one on the left, but does this count as a parallelogram? This part of the definition is the key. It must be a quadrilateral to count as a parallelogram, so this one does not count. It's pretty straightforward. It has to be a quadrilateral. Opposite sides are parallel. Simple. Here I have labeled the vertices of the parallelogram. With the vertices labeled, I can then call this parallelogram ABCD. However, who wants to write out parallelogram all the time? And it gets ugly when students try. 1 R, 2 R's, first L doubled, second L doubled, both L's doubled. Fortunately, mathematicians figured out early on that parallelograms come up a lot, and a symbol was in order. This is the symbol. It looks like a little parallelogram. The sides do need to be slanted. The next idea is to make sure you get what opposite sides are. Officially, this is the definition. However, you don't really need that official definition ever. If you like it, fine, but just use some common sense. These are the opposite sides. They are the sides that are opposite from one another. The red pair, line segment AB and line segment DC, are opposite sides. And the light blue pair, line segment AD and line segment BC, are also opposite sides. That should, hopefully, be obvious. So with that idea of opposite sides in your head, look at all of these parallelograms I have all over the screen. What do you notice about every pair of opposite sides on the whole screen? Do you notice anything at all? The effect is most dramatic on the purple one in the top right. What do you notice about the opposite sides of the purple one? You should notice that the opposite sides are always the same size. That brings us to this theorem. If a quadrilateral is a parallelogram, then its opposite sides are congruent. You will be using this in proofs quite a bit, but it doesn't have an official name. So we need to figure out a good way to abbreviate it in a proof. The structure of the theorem is an if-then statement, so we need to keep that. The important part of the hypothesis is that it is a parallelogram, so that needs to be there. I suggest something like this. It keeps all of the relevant information, and you won't get a hand cramp writing down so much. Write it all out if you prefer, or come up with some other abbreviation. But as a reason in a proof, you will need to write something like that down, since this theorem doesn't have an official name. Now we come to the idea of opposite angles. Like the concept of opposite sides, there is an official definition, but you don't really need that definition. Just use some common sense. These are the opposite angles. The red angles, angle A and angle C, are opposite angles. The blue angles, angle B and angle D, are opposite angles. That should hopefully be common sense. Let's go back to these shapes, but I'll get rid of the filler so we can focus on the angles. Focus on the opposite angles. What do you notice about all of the opposite angles? The effect is most obvious on the one in the middle of the bottom row. What do you notice about the opposite angles of the one in the middle of the bottom row? You should be able to see that not only for that one, but for every pair of opposite angles on the screen, they are congruent, which brings us to the theorem that details just that. Parallelograms have opposite angles that are congruent. Like the previous theorem, it doesn't have an official name, sad face, so we have to abbreviate it when we use it in a proof. The abbreviation I would use is very similar to the last one, with just one word changed. Again, if you want to write it all out, go right ahead. If you want to come up with your own abbreviation, that's fine too, just make sure you keep all of the relevant information. You'll use this in proofs quite a bit too. The concept of consecutive angles is often not as immediately intuitive as opposite sides or opposite angles. Opposite angles are those that didn't share a side, but consecutive angles are angles that do share a side. Many students like to think of consecutive angles as being next to each other. I think it will sink in better if you see what they are, so here you go. Each of these pairs of angles are consecutive angles. But not only are they consecutive angles, they are also something else that is special. Let's run the animation again, but this time think about what other kind of special pair of angles they are. Hint, it has something to do with lines and a transversal. What kinds of angles are these? In a quadrilateral, consecutive angles are also same-side interior angles. And remember that we are dealing with a parallelogram here, so the opposite sides are parallel. And what do we know about same-side interior angles when the lines are parallel? We know that they are supplementary, which leads us into the next theorem. If you have a parallelogram, then every pair of consecutive angles is supplementary. That's simply because every pair is a pair of same-side interior angles, and the lines are parallel. Like the other theorems, this one has no official name, so it needs to be written out as a reason in a proof. You can probably take a pretty good guess at how I would abbreviate it. Use that if you like. This one isn't quite as common as the previous two theorems, but still, It's nice to write less, right? There's one last property of parallelograms, and it has to do with the diagonals, so let's draw them in. This one is a little harder to see than the other ones that we did. Do you notice anything particularly interesting about the diagonals of these parallelograms? As a hint, the effect is most pronounced in the middle two parallelograms, especially the bottom middle one. You may notice that in every parallelogram, the diagonals are both split into two equal pieces. This is the theorem that covers that idea. If a quadrilateral is a parallelogram, then its diagonals bisect each other. You need to get used to that phrase, diagonals bisect each other. It comes up a lot. They cut each other in half, just like I have drawn in the picture below. You can think of it this way too, that their point of intersection is the midpoint of both diagonals. If you like that better, great, but math books everywhere will still refer to it as diagonals bisecting each other, so you still need to be used to that phrase. Like the other theorems, this needs an abbreviation. This one doesn't abbreviate as nicely as the others, but you will only need to use it a few times. This is what I would do. So far we have covered 4 properties of parallelograms. Here is a handy summary for you. You obviously will need to remember all of those. And now the theorem which seems a bit out of place. The rest dealt with parallelograms, but this one doesn't. It deals with parallel lines. Oh well, here goes. Here I have 4 parallel lines, but this theorem works anytime you have 3 or more parallel lines. Let's draw a transversal crossing these parallel lines. I have marked this transversal, showing that it has been chopped up into congruent segments. This means that these parallel lines are evenly spaced apart, so just be on the lookout for a transversal where it has been marked with congruent segments. It's handy to have evenly spaced lines. In fact, many of you probably have lined paper in front of you where you have a bunch of evenly spaced parallel lines on it. If you do, you can use that to demonstrate to yourself that this next effect really does work out, although you should have a straight edge, ideally a ruler, that you draw with. So I have these evenly spaced parallel lines. I have one transversal with congruent segments telling me so. But whenever you have evenly spaced parallel lines, every transversal is cut into congruent segments. You can try this on your paper too. Simply draw a straight transversal that crosses your evenly spaced parallel lines. You should notice that no matter how you draw the line, it is cut into congruent segments. This is the theorem that goes over that exact concept. Remember, you need the first transversal, in my examples it was the black one, marked off as congruent first. That tells us that the lines are evenly spaced apart. But once you have the first one marked congruent, then all of the transversals will be cut into congruent segments also.